All right, so before we start any examples, let's look at our procedure, how we're going to solve these. So first, we have to construct a model for an applied linear programming problem. So the first step is introduce the decision variables, your x's and y's. Then we summarize the relevant material in table form and relate the columns to the decision variables if it's possible. Step three, we're going to determine the objective and write a linear objective function. And step four, we're going to write problem constraints using linear equations and or inequalities. Okay, inequalities are going to be probably more likely what's going to happen because we need it to be less than or equal to the 84 for the assembly constraint or something like that. And then step five, we're going to write non-negative constraints. So basically, our x and y's have to be greater than or equal to 0. Then a linear programming problem is concerned with finding the optimal value. It's going to be either a maximum or a minimum of a linear objective function in the form z. So z equals ax plus by, and a and b not both equal to 0. So we can't have both of them equal to 0. That doesn't really make sense because you wouldn't ever maximize anything. One of them can be, but not both. Now, the decision variables x and y are subject to problem constraints in the form of less than or equal to or greater than or equal to linear inequalities and equations. Now, the decision variables must satisfy the non-negative constraints that x and y both have to be greater than or equal to 0. And then the point satisfying both the problem constraints and the non-negative is called the feasible region. So if you remember that kind of the yellowish region before in our problem, that was going to be our feasible region. Now, any point in the feasible region that produces the optimal value of the objective function is called our optimal solution. So like that 20 comma 6 in our first example for the tense. All right, so theorem one is called the fundamental theorem of linear programming. It says if the optimal value of the objective function in a linear programming problem exists, then that value must occur at one or more of the corner points of the feasible region. Now, sometimes what happens is it's not going to actually be a corner point. It might be a line. So it might go from here to here, and it might be all the points along that line are going to be feasible. Okay, so that's going to be kind of a key thing. Some of them are going to be actually aligned. Now, theorem two says the existence of optimal solutions. So if the feasible region for a linear programming problem is bounded, then both the maximum and the minimum value of the objective function always exist. Now, if the feasible region is unbounded and the coefficients of the objective function are positive, then the minimum value of the objective function exists, but the maximum value does not. Because thinking about that, if we have a graph and say, it's coming down like this and something like this and maybe like that, I don't know, it's not a very good example because that one's below that one, but whatever, and it's unbounded, that means it's everything up here. Then what happens is there's not going to be a maximum because it just keeps going on and on and on forever that way. But we can have a minimum, and that minimum is going to be somewhere like probably going to be either here, here, or here at a little higher, but at one of those places to be the minimum. And see if the feasible region is empty, that is, no points satisfy all the constraints, then both the maximum value and the minimum value of the objective function do not exist. And so that happens as well. Geometric method for solving linear programming problems. So first, we have to have a problem. Then after that, we're going to graph the feasible region. Then if an optimal solution exists according to our theorem two we just looked at, we need to find the coordinates of each corner point. Now, this is when the calculator comes in handy, trying to find those points. And then we construct a corner point table that lists the values of the objective function at each corner point. Then step three, we're going to determine the optimal solutions from the table in step two. And then for an applied problem, we're going to interpret the optimal solutions in terms of the original problem. All right, so that's kind of the steps we're going to follow to solve these. And so let's stop here and then we will come back for our actual problem.